Well, recently I went through a flat earth flyer by Nathan Thompson, discussing every point he made. During that time, I came across another flyer, this time by Flat Earth 101. As they all mostly have the same talking points, I have already covered most of these claims. Section 1 is balloon footage and wide-angle lens. Well, this one was section 4 in Nathan's flyer, and I have a detailed video on it. A card should be popping up now. Section 2 is the aircraft dipping its nose. This was also 2 in Nathan's. Again, a card should be displayed. Section 3 is the one that appears to be different. I don't think so. The law of perspective greatly limits our ability to see far distances. Are we to believe that from 238,000 plus miles away, we can make out features on the face of the moon? Now, I have covered explanation for this briefly in section 10 of Nathan's flyer about boats over the curve. On this, I guess I can elaborate on the explanation. It is an almost fair point, except they had to lie, didn't they, to make their point. Greatly limits our ability to see far distances is quite misleading. But first, can we just establish something? From northern hemisphere, we can see Polaris with naked eye, and we estimate Polaris to be 433 light years away. For those who's not sure what light year means, well, it's the time for light, the fastest thing we know. And special theory of relativity implies only particles with zero rest mass may travel at the speed of light. So it is super fast, and 1 light year is how far it is to travel in 1 year. TLDR, Polaris is really far away, and yet we can see it. At the same time, I have a receipt at the far end of my table. I can see the shape and the large logo, but can't make out the actual writing. I would say the distance is maybe 4 feet. Now, would you consider 4 feet or 1.2 meter to be a great distance? Yes, it is perspective. And the farther I am from that receipt, the smaller it would look. At one point, I will not be able to see it, unless I bring out a Nikon P1000. If you wear glasses, you will by no doubt be familiar with this chart. From a distance of 20 feet, if you can distinguish the letters on the 4th line up from the bottom, you would be described as having 20/20 vision. If you could just resolve the letters 2 rows up from the normal vision line at 20 feet, your acuity would be labeled 20/40. And if you could resolve 2 lines down, it would be labeled 20/10. When it gets to about 20 to 200, I believe that was one condition to be considered legally blind. So what is going on? Well, it comes down to angular resolution, and Rayleigh's criterion shows that the minimum angular spread that can be resolved by an image-forming system is limited by diffraction to the ratio of the wavelength of the waves to the aperture width. That's a mouthful, right? Trust me, it explains it all. Imagine a flat plane. There is no curve. You're viewing a ship going straight away from you. You can make out the boat hull and the mast. As it goes farther away, it gets smaller, and then at one point disappears from view. But wait, the reason we see objects because of the light being reflected from it and coming to our eyes. The light from the ship didn't miraculously stop all of a sudden. We know this because we'll be able to see the ship if magnified. So the light or data is there, we just can't perceive or distinguish it anymore. Let's start with a white piece of paper, and we draw 2 parallel lines A and B on it. How far can you see the lines from? As we move farther away, it gets harder. Imagine a line from A to your eyes, and another line coming from B. The angle those 2 lines make is angular resolution. And Rayleigh criterion gives us a formula to determine what's the minimum this angle can be before we are unable to distinguish. The formula simply is theta equals 1.22 times lambda divided by d, where theta is the angular resolution in radians, lambda is the wavelength of light, and d is the diameter of the lens aperture. The factor 1.22 is derived from a calculation of diffraction pattern. Super easy. The actual reason is diffraction, but we're really interested in this formula here. Our eye pupil diameter changes during day and night, whereas the pupil size is between 3 mm to 4 mm, and at night it is from 5 mm to 9 mm. In addition, the optimal sensitivity of the human eye is approximately 0.55 micrometer. So according to Rayleigh's criterion, we can calculate the spatial resolution of human eye. Let's say that at daytime, the pupil size is 3 mm and the optimal sensitivity is 0.55 micro-m. We can apply the rule, angle is 1.22 lambda divided by diameter, or 1.22 times 0.55 micrometer divided by 3 mm, and that gives us 0.0128 in degrees. So with perfect vision, an average human eye during a day can distinguish 2 points as long as the angular resolution is more than 0.0128 degrees. See how this applies to any distance? That receipt at my table, well, the lines made an angle less than what I can detect. The same reasons I can't count the number of blinds my neighbor has on her Venetian blinds. This formula allows us to calculate some funky stuffs. Like from Hubble Space Telescope, if two stars were 2 million light years away from Andromeda Galaxy, how close can they be and yet still be resolved? Now to our glorious moon. I love that thing. It's a piece of rock, yet so romantic and lonely. To start with, the best time to see the moon is not during its full phase. During full moon, rays of sunlight are hitting the visible portion of the moon perpendicular to the surface, resulting in less surface details compared to other phases when sunlight hits the moon at a much shallower angle. The moon's biggest and most obvious features are its large, flat, grey patches called Maria. This is the Latin plural of mare, which means sea. These are solidified lava flows from between 3 to 3.5 billion years ago, a billion years younger than the majority of the lunar surface. Then you have Montes Apenninus, the moon's highest mountain range extending for over 400 kilometers. Tycho crater, a highly reflective impact crater over 100 kilometers in diameter in the southern lunar highlands. At number 4, we have Copernicus crater, visible as the bright spot amongst the dark Maria, has a 107 kilometer diameter, offers the greatest visual contrast of any lunar crater to human eyes. For number 5, the largest of all the Lunar Maria, it is the only one designated an ocean, Oceanus Procellarum. It covers approximately 4 million kilometers square and contained Apollo 12's landing site. Do we notice something obvious? All these features are quite large. Just for laughs and giggles, I thought I would try out some basic math. I decided to go with Copernicus crater. Given the other sizes, this is the second smallest, but not a highly reflective crater like Tycho. Suppose the Copernicus crater is bang in the middle of the moon from your viewpoint. We can now imagine an isosceles triangle from the sides of the crater to your eye. Now if we divide the triangle into two right-angle triangles, well, we have an adjacent leg, the distance to the moon, we have opposite leg, half the diameter of crater, and we can calculate adjacent angle. Finally, if we multiply that angle by 2, we would get the angular resolution. Earlier we calculated average human eye minimum angular resolution during day. At night, the pupils get bigger, and as the angle is a result of division by aperture, At night, our minimum angular resolution is less than during the day, but it doesn't matter. As you see, from adjacent lake value of 384,400 km, the distance between Earth and Moon, opposite lake value of 53.5 km gives us an adjacent angle of 0.00797 degree. Note that I didn't round it up to 3 digits. Time that by 2 to calculate what is the angular resolution Copernicus crater is making. Well, it's 0.01594 degrees. For those keeping count, it has to be more than 0.0128 degrees for us to be able to distinguish it. So yeah, that checks out. Please note that I didn't take any other variables like surface reflection, atmospheric refraction and so on. This is just a simple math to see if it falls within the range. Well, I hope that clarifies why we can make out features on the face of the moon. That's all for this video. Thank you so much for watching. If you've enjoyed this content, well, a like and a comment won't go amiss. If you'd also subscribe for future contents like this, it would definitely help my small channel grow and would be thoroughly appreciated. Have a safe day, signing off.
We are one people.